So thank you very much. My name is Brevis. I work at the University of Sheffield, and today I'm going to talk and do basically a summary about the activities of the SIG-44 that is focused on multi-scale generate turbulent flows. So just an overview of the activities of the SIG. The research that we are trying to promote within the SIG is focused on the aero and hydromechanics of geometrically complex objects. And those geometrically complex objects, they are classified as multi-scale. We particularly would like to understand the role of geometry on the flow properties, and even more, to try to understand that role very specifically to produce bespoke flows for particular applications. So in that range of applications, we can basically focus in small and large scale flow structures. In this talk in particular, I will concentrate on the fundamental and applied research at two branches of SIG-44, in particular Imperial College London and at the University of Sheffield, where I am coming from. The academics involved at both institutions are listed there. So Oliver Baxton, Sylvain Lassier, and Christos Vasilikos at Imperial College. And in our case at the University of Sheffield, myself, Bernard Brevis, Chris Killock, and Fran Nicoulou. So there are some ongoing research as part of the SIG. At the moment, there is a project based at Imperial College that is a European project called Multisolve, which is focusing on multi-scale solution for industrial flow problems. Christos was awarded an ERC grant to concentrate on fractal generated fluid flows. Oliver recently got an EPSRC grant from the British Research Council to investigate the fractal forcing of axisymmetric turbulent jets. And myself, I'm focused, also funded by the EPSRC Research Council in the UK, investigating the quantification of the influence of fractal and non-fractal group of obstacles in a shear flow. We have had in 2015 some dissemination activities. One of them took place in Sweden, and it was specifically a workshop part of the International Conference of Jets, Wakes, and Separated Flows. And the second activity was a two-day workshop that we were running at Sheffield together with the SIG-42 that was concentrated on multi-scale force turbulent flows. And we got approximately 25 speakers, and it was also streamed online. Right, so let me talk first about the research at Imperial College. One of the fundamental research that is being carried out at Imperial College is related with the flow physics of multi-scale flows, and is concentrated basically on the interacting wakes and fractal grids generated turbulence. And the research is basically focused on flow profiles and velocity derivative statistics. We also have research on wall boundaries, concentrated on understanding heat transfer enhancements and the generation of thick turbulent boundary layers. And also, which is can be quite important for the ERCOFTAC community, are the applications of the multi-scale flows. In that line, Imperial College is researching the improvement of mixing in static and dynamic mixers, and they are looking not only at the flow structure but also at the scalar structure generated by a fractal device. And they are focusing in particular on the characterization of the pressure drop and the power that this device needs to spend. The colleagues at the Imperial College has been also working on improving the performance of aerodynamics devices, and in particular of spoilers and wings devices. And they have been developing and building some fractal spoilers and have been exploring the use of fractal spoilers together with BAE systems. And I have been researching together also, I believe, with the group at Poitiers, the analysis of aeroacoustic properties of the resulting flows. This has been carried out using both numerical and experimental approaches. And finally, from Imperial College, we have the work of Oliver Baxton that is working on fractal forcing of an axisymmetric turbulent jet. The idea is to investigate what is the effect on the jet structure of the shape of the nozzle. And what Oliver has been doing is basically investigating how the physics and depends on the number of corners and wet perimeter of that nozzle. The idea is to try to improve the mixing of these jets and to look at the entrainment properties, and also to investigate the flow energy redistribution. Right, so now regarding the work that we are doing at Sheffield University, this is one of the problems that we are trying to understand. We are investigating turbulent shear flows over multi-scale arrays of surface-mounted cubes. The idea is actually to try to represent some generic geometries of environmental flows, and which is a generic case, let's say, of the flow across complex porous turbulent systems. You can imagine an urban area or a vegetated area. And these areas can be basically represented quite well using multi-scale geometry. And in particular, we are interested in investigating the role of fractal geometry to characterize the complexity of these obstacles, but also to try to find a relationship between that fractal geometry and the flow properties, in particular, scaling of dominant structures. So as part of the work, we are focusing on the identification of coherent structures and their dependence on the geometry, and in particular, one of the main environmental problems that we want to understand is associated to the ventilation of cities. And as a consequence, our hypothesis of work is that the large-scale structures dominate in ventilation. The exchange between urban areas and the atmosphere is connected to the development of coherent structures, which depend at the same time on the fractal properties of the group of obstacles. So at the right part of the slide, you can see a small picture of some of the experiments that we are running at Sheffield, which are concentrated in a generic model of obstacles, and we are investigating the role of iterations, different fractal iterations, different complexities in the vertical dimension on the development of these coherent structures. So most of the work is experimental, and at the moment we are running tomographic measurements of the flow structure, which will give us plenty of detailing insight. Our preliminary results are showing that actually the flow is dominated by coherent structures, and they can be linked to the geometry. And in particular, something that has been highlighted by our preliminary results is the importance of helicity in the flow dynamics in this case. And that importance of helicity is basically being highlighted in terms of the spectral characteristics of these sort of flows. Another line of research at Sheffield is we're interested on understanding the energy dissipation and the wave characteristic developed by multi-scale obstacles in shear flows. The reason why we are interested in this is because we believe that if we understand the link between the geometry of these obstacles and the energy dissipation properties and the flow structure properties, we will be able in the future to design engineering structures that can actually be a bespoke design to control some environmental flows. So our objective is the quantification of the large-scale turbulent structure produced behind these waves, and to do that, we are basically using as a benchmark a regular obstacle. Now, for this, we were using a three-dimensional velocimetry system that is being sketched at the bottom right part of the slide. And with these results, we have been investigating the role of some fractal properties that you might not be familiar with them, but they are quite easy to obtain, which are the fractal dimension, linearity, circularity, and other parameters that we use to represent these complex geometries. So again, the objective is quite similar to the one before, and we have obtained some results, and the results are shown in the figure. These results are basically showing a comparison between regular arrays of obstacles and multi-scale array of obstacles that involve the same solid fraction. That means that the amount of material invested on the construction of this obstacle is quite similar, and we have seen actually quite dramatical benefits of the multi-scale selection on the characteristics of energy dissipation. Another line of research is led by Frank Nicolau, also at Sheffield University, and is related with the development of some new devices for the measurements of flow in pipes. So we want to actually, the challenge is to try to measure the flow rate, the discharge in pipe flows. And for this, normally people make use of instruments, and the challenge is try to do those measurements, minimizing the effects on the flow, in particular minimizing the effect of the pressure drop. So the most common approach for this, which is normally used in hydraulics, is to use some orifice plates which are sharp edged. Now, this is normally the way to do it because they are simple and there is no mechanical parts. However, many people in the industry know that they can produce quite important energy losses. As a consequence, the challenge is try to minimize that permanent pressure loss induced by the device. So, in this respect, Venturi can be an alternative, but it's a complex device to install in existing facilities. So the approach that was decided to follow was to change the design of the orifice in try to optimize the orifice shape. And the improvement that we are looking for is actually try to shorten the recovery length and try to shorten the pressure loss. So on the right part of the picture, you will see that there are two approaches. One approach is to develop a so-called fractal perimeter orifice, and the second one is basically to make use of fractal perforated orifice. So I'm going to talk basically now about the first one, the fractal perimeter orifice. What you see on the slide are results from numerical simulations showing the pressure drop associated to the different shapes. And very shortly, what you can see here is that SF3, which is the fractal shape with a larger number of iterations in the perimeter, is the one that actually is inducing the shorter pressure drop. And as a consequence, we are starting to hit one of the challenges that we thought at the beginning. And it seems that some physical mechanisms developed by the fractal shape are actually able to reduce the pressure drop. So the question was actually what kind of mechanisms are actually triggering this sort of behavior. And for this, large A simulations were used. And you can see here, starting from the top left corner, normal orifice plate, follow it on the right side by a triangular shape, and then basically adding iterations to that triangular shape. And as you can see on the top two ones, is clearly, we are now looking at isosurface of lambda 2 for an instantaneous picture of the flow. We can actually see the development of some massive structures. which might explain the development of those structures, might explain then the pressure drop associated to this type of orifice plates. Now, basically the experiments and the simulations have revealed that there is quite a complex vortex evolution, and there is a self-induction and the interaction between azimuthal and axial vortices. So the picture at the bottom of the slide basically showing the characteristics of different shapes of fractal plates for different downstream lengths respect to the obstacle. So in the first one, a position x0, we see basically the imprinted shape of the orifice on the velocity contours. Then at 0.25, we can see that the contours begin to blur. At 0.5, we start to observe the switching on the fractal orifice. When I'm talking about switching, I refer to the axis switching. And then at position x divided by b equal 1, we can see that the triangular shape have already inverted his position, but the orifice 1 remain without any change. Another line of research that we are running at Sheffield is linked to, that was already performed by Chris Kellogg at the University of Sheffield, was the analysis of the wake structure of fractal fences, which are normally used to protect highways against wind gas, and in particular in this application was to try to reduce the amount of snow that you will see on top of a street. So basically, the idea of this research was to look at the fractal properties of a fence and see what would be the possible benefits of having a fractal fence. So in the picture, you see the measurements that were performed in Japan in a quite special wind tunnel that allows the measurements with snow. On the right side of the slide, you see from the top to the bottom the different types of fences that were tested. And at the bottom picture, you see the results of some of the trials, where you clearly see downstream the fence a zone without any snow. So they know the accumulation of snow is basically shifted downstream. So here are some results, and what I'm showing on the top part of the slide are the results of longitudinal profiles of the amount of dissipation calculated to be occurring at what was supposed to be the inertial regime. And we can see that there are different behaviors first. So what you see for the plus line type is basically 5 struts and 50% porosity. The asterisk is 50% porosity and 9 struts. And then basically we have the fractal fences, which are shown in the picture. So basically we see that the decay of energy in this case is quite different for the fractals and the non-fractal fences, which basically was difficult to understand. And one of the explanations for this basically was that fractal fences are dissipating energy, and this dissipation will limited, and they were showing dissipation beyond what was expected to see from the von Karman and Howard theory. So, and we saw this difference, and we think that the forcing by small struts is actually inducing this. So this will be the end of my presentation. Basically, what I would like to comment to summarize the activities of the SIG is, in the previous years, we have invested a lot of effort to try to understand the fundamentals of the flow, the role of force signal spectrum at different scales. And now we are in a stage where basically we are starting to see a lot of research taking place on the applications of this sort of properties. And we believe that this is not only going to have an impact in the academia, and actually we can see applications at a very broad range of scales. Thank you very much.